Hopefully you remember Newton's first and second law. Remember, Newton's first law was an object will stay at a constant velocity unless acted upon by an unbalanced force. Newton's second law, of course, is just an equation, and that is that net force, which is the sum of all the forces, is equal to mass times acceleration. And then we have Newton's third law. What is Newton's third law? And that is for every action there is an equal and opposite reaction. I'm sure you've heard that before. So we just saw this in our attached objects questions with the pulleys and the trolleys. When the heavier mass went down, what happened to the other mass? It went up, or it went along the surface. So there was that equal and opposite reaction happening. So every force has an equal and opposite force. Okay, so when you push an object, the object is actually pushing you back with equal force in the opposite direction. Okay, so basically if you have the force of object A on object B, then B is going to push back on A. So that's equal to negative force, right? So they are equal and opposite. They're equal, but just in different directions. Now, a lot of people say that, okay, well, when I'm pushing on a box, then is the equal and opposite force the friction? Because I don't think it's actually equal and opposite. It's not actually. So when you push a box, so here we have the person pushing the box. So I'm going to draw an arrow like that, of course. So that's my force of the person on the box. I'm just going to say PB, person on box. The frictional force going in the other direction is not the reactive force. What's the reactive force is the fact that the box pushes back on the person, which is why we need to apply force to move it in the first place. Okay, and then we'll have the box pushing on the floor, so it'll be pushing that way. So we'll say BF for box on the floor. And then the floor, of course, pushes back on the box, and that's our frictional force. Okay? So those are your equal and opposite reactions, not the pushing and the friction. Those aren't equal and opposite, because as we know, if you push more than the friction, then the box moves. So it's actually the fact that the box is pushing on you, and that manifests itself in the fact that if you stop pushing the box, guess what? It's going to stop moving, right? So when we're applying Newton's second law, so far we haven't actually taken all these forces into account. We've really been looking at the forces acting on the object, okay, which is the red arrows here. Okay, so if we're looking at Newton's second law, then of course why we think that the frictional force is the reactive force is because those are the only ones we really care about, is the force that the person applies and then the force of friction. And that's all we really care about in Newton's second law. But when we're actually looking at Newton's third law, we're looking at what's happening between the box and the person and the box, right? And the floor and the box and the box and the floor. So we have to think about those as our reactive forces. Okay, so of course this box is going to move only if the person applies a force that's greater than the force of the floor in the box, which is of course friction. Okay, so that's not our reactive force because we know we can unbalance those forces. Okay, so when we're doing Newton's third law questions, well, we've already done some. So for example, our attached objects, that is Newton's third law. We are using the fact that there is this reactive force, right? When force of tension pulls one mass down, it can pull the other mass up if they are connected over a pulley. And the fact that the tension is the same and the acceleration is the same are the equal and opposite reactive forces. Okay, some other ones we can do is recoil type questions, and that's, you know, if you have a rifle or a bullet, or you're even just throwing something and it pushes you back a bit, that is Newton's third law, and so we can just go right ahead and say, okay, well, the force of for example, the rifle and the bullet is equal and opposite to the force of the bullet on the rifle. Okay, and then we have the objects in contact, which is like this kind of right here, where we have to then consider the forces between the objects, okay? And so then we have to start with Newton's second law and then, you know, go from there. So we'll get to that, but let's start with this guy. So when a rifle fires a bullet, the rifle kicks back. So again, we know bullet's going forward, rifle is going backwards. It has that recoil. So we have a 15-gram bullet, which make sure you change that to kilograms, is fired from a 6-kilogram rifle with 75 centimeter long barrel. Okay, that's a weird thing to get. So we want to determine the acceleration of the rifle if the bullet leaves the barrel with a speed of 70 meters per second. Okay, so we're actually given some kinematics kind of information about the bullet. So we're seeing actually how far it has to go to get to 70 meters per second. So this is actually the displacement of the bullet. And here's your final velocity of the bullet. Guess what? Its initial velocity is 0, because obviously it starts from 0 and gets to 70. So that's why it gave us that information, because it looks like I need the acceleration of the rifle, but I don't have the acceleration of the bullet, but it looks like I might have enough information to find it. So we're going to use that. But first, let's just start with Newton's third law. I know that the force of the bullet on the rifle will be equal and opposite to the force of the rifle on the bullet. Okay, and then force, we're just talking about net force here, so that's mass times acceleration. So that's mass of the rifle times acceleration of the rifle should equal the negative mass of the bullet times acceleration of the bullet. Okay, now we don't have the acceleration of the bullet, so we do need to find it. So we have displacement, we have initial and final velocity, and we're looking for acceleration. So basically any kinematics equation that doesn't deal with time, and really there's only one of those, and that is this guy. So I should be able to find acceleration with this. My initial velocity is 0, so I can go ahead cross that out right now. So I get the acceleration of the bullet should be equal to its final velocity, all squared, divided by 2 times its displacement. Okay, so I'm going to go ahead and substitute that in for the acceleration of the bullet. So this guy can go right in there. Okay. So I have the mass of the rifle times acceleration of the rifle equals negative mass of the bullet times VF squared divided by 2D. So I'm just going to make this into one full fraction there. And then I need to divide by mass of the rifle in order to get the acceleration of the rifle. So my final equation looks something like this. And I can plug in the numbers. Mass of the bullet, remember, is 15 grams. So divide that by 1,000, and that's 0.015 kilograms. My final velocity was 70 meters per second. Got to square that. Don't forget to square. 2 times my displacement was 75 centimeters, which again I need in meters, so that's 0.75 meters. And the mass of the rifle was given in kilograms, so I can just keep that as is, and I get an acceleration of negative 8.2 meters per second. Makes total sense that the acceleration here would be negative because, of course, the acceleration of the bullet we're going to assume is positive since it's going forwards and the rifle is going backwards. Okay, so that's how you deal with recoil questions. And that's what you're more likely to see. So this next question, you're not as likely to see on tests or anything like that, or the diploma. It would probably be a higher level question, possibly an AP question, but let's still go over it just to see. So here is an example of 2 objects in contact being pushed. So the 2 boxes are being pushed to the right by a 25 Newton force. Okay, so what makes this difference from just pushing a box? So if it was something like this, again, we only care about the forces acting on the object, but there's only one object, so we can just use Newton's second law as we normally would. But now when we're looking at the forces acting on the objects, well, the blue box is exerting a force on the red box is exerting a force on the blue box. So we kind of have to keep that in mind in our when we're using Newton's second law, that we also have the third law at work here, which it's always at work, but now the way it's at work, we need to consider it in our calculations. Okay? So we have a coefficient of friction, meaning, of course, there is friction here. So that's 0.35. So we need to determine the acceleration of the boxes and the force of the red on the blue. Okay? But the thing is, think about it. Equal and opposite. So the force of the red box on the blue box, is that going to be the same as the force of the blue box on the red box? Absolutely, they're just going to be in different directions. Okay? So something for us to consider. So I'm going to draw free body diagrams here. I'm actually going to do them separately because I don't want it to get too messy. And might as well do a blue free body diagram for the blue box and a red one for the red box. I think it just makes so much sense. Okay, so here's my blue box. Obviously have normal force going upwards because it's on a surface and gravitational force going downwards. And then, of course, there's an applied force, which is being pushed to the right. So there's applied force going right here. Okay. And there's a frictional force going to the left. But what else is there going to the left? The force of the red box on the blue box. Okay. So that's something that we should probably keep in mind. So my applied force would likely be larger than this to actually have to be able to push this. So we'll make this a bit longer because it's still moving to the right. Okay, so that's what the free body diagram for the blue box would look like. Let's look at the one for the red box. Okay, so here we go. Same thing, we have a normal force going upwards and a gravitational force going downwards. Okay. So what do we have here? We have the force of the blue box on the red box is actually kind of replacing our applied force because the applied force is on the blue box. It's not on the red box, which I get, that's kind of annoying. And if you put applied force here, would it be wrong? Not necessarily, but I want to consider it as the force of the blue box on the red box. Because remember, we're actually pushing the blue box, which then in turn is pushing the red box. Okay? And then, of course, we have force of friction moving in the other direction. So I should probably actually decipher between red and blue. So I should probably call this force of friction on the red box specifically. So I'm going to do, oh my goodness, I cannot write right now. Okay, so that's FFR. If you can't read that, I'm sorry. And then force of friction, and I'm going to put a B there so I know that's for the blue box. Okay, doesn't this look fun? So, as we did in our attached objects questions, we need to treat these as separate, right? So I'm going to start with the blue box and then with the red box, and then we'll go from there. Okay, so when we're looking at our blue box, let's do Newton's second law there. Sorry, just want to get the black pen. So obviously it's moving to the right, so I'm going to say right is positive. And I know the sum of my forces should equal to mass of the blue box times acceleration. Some of my forces, well, I had applied force going to the right, so that's positive. And then going to the left, I had the force of friction and the force of the red box on the blue box. Yeah, it's going to be really fun. So this is for the blue box, and then minus the force of the red box on the blue box, because of course the red is going to push back a little bit on the blue. Okay, so what are we going to do here? There's a few things we can do. First of all, force of friction. We can figure out that because it's mu Fn, and of course we can find Fn. But for the force of the red box on the blue box, I have no idea, right? So really what I can do here is Fn, and that's for box B. But this guy, no idea. And I'm looking for acceleration. Okay, so what do you do when you get stuck? You go over to the other direction, or you go over to the other object, which is I'm going to do here. I am going to eventually get normal force, but here I'll even do it right now for both boxes. If we go over to the y direction, I know that these are not moving up or down, so that's 0. So I know normal force minus gravitational force is equal to 0. And therefore, I know my normal force is equal to mass times gravitational acceleration. So I'm just going to do that right now just to get it out of the way because I know I'm eventually going to need it. Okay, so let's look at the red box now though, because we're going to go over there and see if I can get some sort of term for the force of the red box on the blue box. Because the thing is, I know something special about the force of the blue box on the red box. Right? Right. So let's go over to looking at the red box and seeing if that's going to help us at all. So again, it's also moving to the right, so I'm going to make that positive. So sum of forces, oh, I should probably call this red. I should probably say B there for blue. So mass of the red box times acceleration. And so what were our two things there? Well, we had the force of the blue box on the red box, and we then had a force of friction on the red box, and that's equal to mass of R, the red box times A. So again, what do I know about force of the blue box on the red box and force of the red box on the blue box? I know they're equal and opposite. So if I come up with a expression for force of the blue box on the red box, can I substitute it in? I absolutely can. Okay, so I'm going to do that. So what am I going to do? I'm going to take mass of the red box times acceleration, and to that I'm going to add the force of friction. What is force of friction? Mu Fn. What did we find out Fn was? It was mg for both of the boxes, but since this is the red box, it's mass of the red box times g. There we go. So I found that this is an expression for the force of the blue box on the red box, which is this equal and opposite to the force of the red box on the blue box. I don't actually have to account for the fact that it's opposite because we already did. It's minus there, it's positive here, so it's already accounted for. Okay, so I don't need to make this negative because I will just by the fact that we're now subtracting it. Okay, so now we can go back and substitute that in and hopefully solve for acceleration, because that's what we want. We want the acceleration of the boxes, and then we want the force of the red box on the blue box, which is equal and opposite to the blue box on the red box. So basically, I need to solve for this once we're done. Okay, let's do this. Hopefully by this time, you've done so much substituting that it's not a big deal. I'm, of course, going to replace normal force with mass times gravitational force, of course, but with mass of the blue box here. And then I'm going to subtract this guy. Make sure you subtract every term. So that's minus MRA minus mu MRG equal to mass of the blue box times A. Now I need to solve for acceleration, which, okay, we just get everything with acceleration on one side of the equal sign and everything over on the other side. Of course, what do we do there? Well, then we factor out an A. And I really hope you're not going to make me do this again. So I'm going to skip kind of a step, or I won't skip it. I mean, I wrote it down, but now I'm gonna just do this because I don't want to have to write the whole left side again if I don't need to. I'm sorry, but it's just what's the point? So at some point, if you can start skipping a few steps with the rearranging, I forgive you, but you could only do it if you know you're not going to make a mistake. If you're I could still make a mistake here, too bad. Then you got to put in the time of writing out every single little step. It's only until you've done it a million times that you can earn the right to not do every little step. Okay? Okay, and that is how we solve for acceleration. And now I do, in fact, have all these numbers, so I'm just going to plug them in. Okay? So the applied force, if you forget what it was, which is fine, because that was a long time ago, it was 25 newtons. So we start with that, minus mu mass of the blue box times g, so mu was 0.35. Mass of the blue box, wow, I just forgot everything, it was 4 kilograms. Times g, 9.81. I'm going to run out of room here. Gonna have to stop writing all the significant digits. I'm sorry. Mass of the red box was 2.5 kilograms. Oh, I'm gonna even skip the units in this one. But yeah, that's what happens when you run out of room. And then mass of the blue box, again, was 4 plus mass of the red box, 2.5. And I should be able to get my acceleration there. And I get an acceleration of 0.41 meters per second squared. There's my acceleration. Wow, all that for that measly acceleration. My goodness. Okay, and then I'm not done because it said determine the acceleration. Check, we did that. And the force of the red box on the blue box, have not done that. So F, force of red on blue, but again, the force of the blue on the red is the same, and then it's just in the opposite direction. Okay? So in both of these cases, right is positive, so the force of the red box and the blue box is going left, so we just get this answer, and then we make it negative, right? We just get the answer for this guy, but then we make it negative because we know this is going to the right, but the force of the red box on the blue box is going to the left. So that's really all we have to do. Okay? So let's do this. I don't know where I'm going to do it because I've run out of room. I guess I'm going to do it down here. Okay? So we know force of the blue box on the red box is equal to the negative force of the red box on the blue box. So what I'm going to do, I'm going to multiply this whole thing by a -1. Okay? So then we have MRA, so mass of the red box was 2.5 kilograms. How am I doing this? I'm reading it from here, by the way. 2.5 kilograms times my acceleration, which I got was 0.41 meters per second squared, plus mu 0.35 times mass of the red box, which again was 2.5 kilograms, times g. And again, I'm running out of room just everywhere. And so what do we get here? Well, here this 2.5 times 0.41 plus 0.35 times 2.5 times 9.81, we get a positive 9.6. But of course, then we just make the whole thing negative, just multiply the whole thing by -1. And so the force of the red box on the blue box is negative 9.6 newtons. Okay? And there we go. We got it all. We actually did it. Woohoo! So that would be probably a good example of more of an AP question. Okay? But that's that. That's Newton's third law, and we are done all our lessons in the dynamics unit. So, yeah, I hope you enjoyed it as much as I did. I really did enjoy it. Love Newton's laws. They're brilliant, and I'm really excited to go on to circular motion with you guys.